I'm Daniel. In this paper, we introduced EGFC, an evolving Gaussian fuzzy classifier and algorithm for never-ending semi-supervised learning based on data streams. We have shown an application example on power quality disturbance detection and classification. So the objective of this paper is to introduce this new method to semi-supervised learning from data streams. It is called Evolving Gaussian Fuzzy Classifier. We have an application example, classification problem with 5 classes, the normal condition of a power system, and 4 types of disturbances: spike, notching, harmonic, and oscillatory transient. We considered landmark time windows, and we extract features from voltage waveforms using the Hodrick-Prescott filter and the Fourier transform. The features of the EGFC method is that it is able to learn in non-stationary environment, in data stream, time-varying environment. It does not accumulate data. We are talking about sequential learning. We use recursive equations in the procedures of the algorithm. The algorithm can process partially labeled data. We can consider fully unlabeled or fully labeled data sets, or any case between these extreme cases. We're talking about the online paradigm, where we can adapt not only the parameters of fuzzy rule-based models, but also the structure. We can add, delete, and merge rules over time. The information granules and the local models, the fuzzy rules, can be linguistically interpretable if we associate linguistic values to fuzzy sets. So we use Gaussians. These are fuzzy Gaussian fuzzy sets, and in general, this is a Kaggle-Sugeno fuzzy system of 0 order. I'll not give the equations, just the summary of the algorithm. We have some meta parameters which are adaptive. We update along the iterations of the algorithm. We have a loop of the data stream. We will simulate a data stream, but it can operate, of course, if one sample at a time become available. So first we provide an estimation. We read the input X and provide an estimation to it. And then if the label, the true label related to X is available, we can proceed in a supervised updating step, or if the Y, if the label is not available, we can proceed in a supervised label learning step. We have 3 procedures, that is parametric and structural adaptation, and after that we can learn from intergranular information. We can reduce the structure and adapt the hyperparameters over time. Notice that in both, to adapt the structure and the parameters of the rule-based model, we have a conditional. We have conditionals that depends if the label is available or not. So we have different equations for any case. We consider a distribution system, 60 Hz, a power grid with 13.8 kilovolt, typical distribution system. We have 5 classes: healthy conditions, spikes, notching, harmonic, and oscillatory transient. We evaluate 3 different window lengths, windows of the voltage waveform. We have a balanced classification problem with 2,000 waveforms of each of the classes. And we also analyze the noise. These are typical values of noise in distribution systems from 20 to 60 decibels. This is the feature extraction procedure. We use Fourier transform and the Hodrick-Prescott filter. This is an example of the five classes we have in the problem. So we have 4 attributes that we extracted from 4 cycle. You can see here 4 cycle time windows, or we also analyze 10 and one cycle of this voltage waveform. So the first attribute is the amplitude of the fundamental component, where you can see here in the Fourier spectrum at 60 Hertz, right? We notice small differences in this amplitude for examples of different classes. So we can use this as a potential discriminative attribute of the classes. The other X2, X3, and X4 are based on the minimum, maximum, and effective or energy that we can calculate based on the time window. This is the minimum value of the time window, the maximum, which is at this point, and the effective value is the energy of the signal. So we extract these X2, X3, and X4 attributes from any of these examples, and to compose input vectors to be given, to be fed to the EGFC model and algorithm. This is the results. So we analyze different levels of noise and different cycles, different lengths of time windows. We notice this is the hardest case. We notice that 10 cycles of time windows gives the best accuracy, but using only 4 cycles of time windows, we have a relatively almost as good accuracy as that of the 10 cycle time window case, using a similar structure and similar processing time. So because this is 2.5 times faster than this, we can achieve a faster analysis rate using 4 time cycle windows at the price of a small reduction of accuracy. So there's a trade-off between these two conditions, and we consider this condition as being the best. This is the confusion matrix. We have that most of the confusions is between classes 1 and 4 because this is the health and harmonic condition. The harmonics are subtle changes of the voltage waveform, so we confuse these cases, and we can see in the final model, this is the final Gaussians of the EGFC model. We notice that classes 1 and 4 are quite superposed, the Gaussians, here in all the 4 dimensions of the problem. So it is difficult to find a decision boundary between the classes that will give more accuracy than this, 92%. And if we do that, in practice, it will not work because it will be overfitting. So we consider this accuracy as being quite good to this problem. This is the supervision spectrum. So this is when the data set is fully labeled. This is when the data set is fully unlabeled. We have a reduction of 6% in performance. Of course, we have less information in this situation. So, but it is, the inclination is not very sharp. We have an algorithm that operates in the whole spectrum of supervision possibilities. We notice here in this curve that the 1 cycle time window loses a lot of information compared to the 10 and 4 cycle time window. So we consider the blue, the red curve as being the best because it saturates in this level of accuracy. So to conclude, we introduced a new semi-supervised string algorithm called the EGFC, Evolving Gaussian Fuzzy Classifier. We have shown an application example on power system fault detection. We have five classes with typical faults in these systems. We considered for the first time their smart grids, the Roderick-Prescott filter, and also the Fourier transform. We extract 4 attributes to give the inputs to the EGFC model. We analyzed 4, 10, and 1 cycles of time windows. We noticed that 4 cycle is the best. The accuracy saturate if you use more information than this, and one cycle is not enough. The noise does not affect the classifier. We notice that the length of the time window is much more important than the noise. And actually, when we use the energy of the cyclical component of the Rodrigues-Prescott filter, we actually, well, it is a filter. It has a filtering effect. So noises start to become suppressed, especially looking to the variable x3. So 4 cycle time windows is enough, and noise does not affect because we have such noise suppression in one of the attributes of the problem. We analyze all the spectrum of supervision. We notice there's a reduction of 6% when all the data set is unlabeled.